we're going to find the half-lives of the following substances. So this first one decays at an annual rate of 5.471% per year. Okay, so that means we're looking at a Q is equal to AB to the T form, so standard form because we're getting an annual rate. And my B here is going to be 1 minus, because we're decaying, 0.05471. When I subtract those, I'm going to get B is 0.94529. Okay. So I've got my B, and that means that I know that this is A times 0.94529 to the T. I want to find the half-life. So the half-life, remember, is the time it takes for half of the substance to disappear. So that would be 0.5 of A. Okay. Those two A's will cancel, one on each side. So that leaves me with 0.5 is equal to 0.94529 to the T. And from here, I'll apply the natural log to both sides. And that allows me to bring that T down in front. Okay, so I get ln of 0.5 equals T times ln of 0.94529. And then to get T, I'm going to divide this over to the other side. So T will be ln of 0.5 divided by ln of 0.94529, which is approximately 12.32. And this is measured in years, so that'll be 12.32 years. All right, the next substance decays at a continuous rate of 10% per week. I'm going to have you work on this one, but I just want to call your attention to that continuous. That means you're going to use this Q is equal to AE to the KT, and K is a negative 0.10. Okay, so you think that should give you everything you need. You're going to do the same idea, 0.5A is equal to A times E to the KT, and see if you can solve there for T. Okay. All right, so pause the video, give that a try, see how you do with that. All right, so hopefully you gave that a try. This is going to end up being 0.5A is equal to A times E to the negative 0.1T. And both those A's will cancel just like they did on the other one. So you get 0.5 is equal to E to the negative 0.1T. Okay, and on this one I'm going to use ln. On this one I could have used log or ln. It doesn't matter which one. But on this one it's going to be better for us to use ln because ln and E are inverses here. So ln of 0.5 is equal to ln of E to the negative 0.1T. And since ln and E are inverses, that means this simplifies to just negative 0.1T. Okay, so ln of 0.5 equals negative 0.1T. So T is ln of 0.5 divided by this negative 0.1. That's going to give me approximately 6.93. And this one is measured in weeks. So this would be 6.93 weeks for this substance to decay half of its amount. All right, number 8, we're going to put together the things that we learned with the Twinkie problem and what we just did with these half-lives to kind of combine all of this together into one problem. So 70% of a radioactive substance decays in 5 hours. How long will it take until only 10% of the substance remains? Okay, so let's start with this 17% decays in 5 hours. So I'm going to use this to help me find B. And so if 17% goes away in 5 hours, that means 83% is left over. So 0.83A is equal to AB to the 5th. So after 5 hours, 17% goes away, so I'm left with 83%. Okay, so hopefully that makes some sense how I came up with that. These A's will cancel. So 0.83 is B to the 5th, which means B is 0.83 to the 1/5 power, right? Or the 5th root of 0.83. And if we crunch that in our calculator, we get approximately 0.9634. Okay, now you get some rounding error when you don't just stick with this as B, but I also understand that that looks super confusing when you try and plug it in. So if I wrote this as Q is A times 0.83 to the 1/5 to the T, I totally understand that that looks a little bit intimidating. This is the better way to go. So if you feel comfortable with your algebra skills, this is definitely a much better way to go because you're going to get an exact answer. If you're going to do the decimal approximation, you want to use, especially if you're going to use it in another calculation, which we're going to do in a minute, you want to go like 4 decimal places. Okay, that way you lose a little bit of accuracy, but not too much. All right, we will use this, and then I'll tell you what the difference is between the number we get using this one and the number I got using that one. So our formula here then is really going to be Q is A times 0.9634 to the T. So that's what we're going to use. And now what we want to know is how long will it take until only 10% remains? So here we did half of it, so 50% remains, so 0.5. Here we want to know when we get down to just 10%. So instead of 0.5a, I'm going to use 0.1a because that's 0.10, right, or 0. So that'll be our 10%. And that'll be equal to a times 0.963, oops, I wrote those out of order, 9634 to the t. And again, both those a's disappear. Right? And now I'm going to apply the natural log to both sides. You could certainly use regular common log. That would work too. 9634 to the t. So ln of 0.1 is equal to, when I apply ln, I can use that law of logs to bring the t down in front. So I get t times the natural log of 0.9634. And then to solve for t, I'll just divide this ln of 0.9634 to the other side. So t is ln of 0.1 divided by ln of 0.9634. And that comes out to be approximately 61.75. And then let's see what our units are. So here we're measuring everything in hours, so this should be in hours. So 61 hours is probably about 3 days or so. All right,